All right, so good afternoon, everyone. We're going to start for today. So first off, I guess let's start with the administrative stuff, right? So today we're going to talk about section 5.4. There's really not a whole lot to section 5.4. So today we're going to take a little bit more of a relaxed pace. We're going to do a little more group work, and it would be maybe a good opportunity if you have some questions over the previous sections that you want to discuss, then maybe we can talk a little bit about those. But otherwise, we're just going to keep working through the notes. I have office hours today from 3 to 4:30 as usual on Microsoft Teams. I've been seeing more and more people come into those, which is great because that's probably the most helpful thing that you can do for yourself if you feel like you're struggling a little bit. Other than that, there's SI sessions. There's a homework due today, which is I think 21 questions long, on 5.1 and 5.2. I'm going to post a homework for 5.3 and 5.4 hopefully today. And the next quiz is going to be quiz 7, which I think is the last quiz, on April 19th, which is 1 week from today. It's going to cover sections 5.2, 5.3, and 5.4. So whatever we cover on Thursday is not going to be on the quiz on the following Tuesday. Also I got some anonymous feedback on the survey which said, well, the question was, can we make the final exam just only about what we're doing right now and not comprehensive? And well, the answer is unfortunately no. Thank you. We can't do that, but what I will do is the final exam will have a bit more of a bias towards the more recent stuff, right? So probably it'll be something like 8 questions and like 4 of them or so will be from integration, and then maybe 2 questions on differentiation and min-max theory, and then maybe like a question or 2 about average rate of change or something like that. Okay, so maybe what I'll do is I'll post before the final exam, I'll do our usual practice exam. I will do a bullets, and I'll also send you some info about the exam in terms of where the questions are coming from. So I'll let you know how many questions are from like which chapters and stuff.
Yeah, I wanted to remind everybody that I also have a session today at 6, and it's going to be in mezzanine 2. It's at the top floor of the library. So for this week, it's going to be today, Wednesday, Thursday, all at 6 p.m.
Okay, so this week, SI is Monday, Wednesday, Thursday at 6 p.m.?
No, Tuesday, Wednesday, Thursday. I didn't have one yesterday.
I see. Tuesday, Wednesday, Thursday, 6 p.m. in what building?
On Tuesday, it's mezzanine 2, and Wednesday, Thursday, it's close heat as usual. I know it's confusing.
How the hell do you spell mezzanine? Is it M-E-Z-Z? Did I spell mezzanine right?
I have no idea.
Hell yeah. Okay, mezzanine 2?
2, yeah.
Okay, and then Wednesday, Thursday, the normal room?
Yeah.
Wednesday, Thursday, normal room. Okay, so a bit of a different SI session this week. So just be advised, I guess. Any administrative questions before we start in on content for today? All right, cool. Then let me just remind us what the hell we were talking about. So last time we were talking about integration, and we discussed what it means when I write down something like this, okay? Which the way we say it is we would say the integral from a to b of f of x dx. Okay, and we had the anatomy of this thing, which said that, okay, the numbers a and b are from are the point, A is going to be the point where we start counting area, and then B is going to be the point where we stop counting area. So it's the area underneath f of x from A to B. Okay, and it was defined to be the limit of the Riemann sums as the number of rectangles goes to infinity. Okay, and in principle, what that gives us is the more rectangles we use, the closer that the area of the rectangles is going to resemble the true area under the curve. So the integral is what we refer to as the true area under the curve, and we can approximate that area under the curve using a Riemann sum. Okay, so for the rest of the class, we're going to be kind of concerning ourselves with this integration concept. We're still going to do a little bit of Riemann sums, but soon enough we're going to learn a much better way of computing integrals that isn't going to rely on Riemann sums. But you still need to know how to do Riemann sum approximation. There will probably be a question on the exam about Riemann sums. I mean, I don't know why I'm saying probably. There will definitely be a question on the final exam about Riemann sums. So you'll need to be able to compute those. So what did we learn about integrals? We learned some rules about integrals, okay, which was, okay, if I take two functions and I add them together and then I integrate, then I get the same thing as if I just integrate one and add it to the integral of the other. So that was one linearity rule. And it's kind of similar to the linearity of derivatives, right? You can, for derivatives, the derivative of a sum is the sum of the derivatives. Same deal for integrals. And same deal for constants. They can be pulled out of an integral. Okay, then we also had switching bounds is going to give us the negative of what we had before. Okay, so if we go from A to B versus if we go from B to A, then we're going to pick up a minus sign. And this third one was sort of intuitive. It just said, okay, if we have 3 points, A, B, and C, right? If we count the area from A to B, and then we add the area from B to C, then what are we going to get? We're going to get the area from A to C. Okay, so that was all that this third rule said. And then, of course, the area underneath the 0 function is just 0, right? Okay, so those were just some rules that we learned. And then we learned kind of one more concept in that class. Okay, 2 more concepts. The first of which was, how do we deal with area which is beneath the x-axis? And the way we do that is we kind of modify our definition of the integral to be, okay, it's not just the area under the curve, it's the area which is above the x-axis minus the area which is beneath the x-axis, okay? Which means that sometimes when we do these integrals, we're going to get a negative number. But that's not strange. Okay, why would you think that that is strange? You might think that that is strange because if we're talking about areas here, if you think of negative area, it doesn't really make sense, right? But if you think of what an integral represents in terms of an accumulation of change, it's very possible for a substance to have a negative rate of change, right? That substance could be decreasing in time, right? And so if the substance is decreasing in time, then the accumulation of this decrease would be a net loss of the substance. So it has a physical meaning. Okay, so somehow I feel like I'm saying that more for myself than for anyone else. Okay, anyways, the last thing we learned was how do we find the area between two curves? And we noticed that the area which is between two curves can be visualized as the area underneath one of them, and then we just take away the area underneath the other one. And if we take away this bottom area, then we'd be left with just whatever was in between. Okay, so that was how we found out that the area between two curves is given by the integral of f of x minus the integral of g of x, which in light of our linearity rule was just the integral of from a to b of f of x minus g of x dx. And the important thing to remember about doing area between curves is the top function has to come first. Okay, so if it turns out that g was actually above f, then we would need to do integral of g minus f, right? It needs to be whichever function is on top minus whatever function is on bottom. Okay? So that was what we learned last time. Today we're going to learn something new, but I had to go through this last part kind of quickly, so I want to pause and say, are there any questions about this area between two curves concept? Would we like to see an example of an area between two curves problem? Okay, let's do a quick example. Okay, let's do problem number 5. Okay, we're supposed to estimate the area between the curves y equals x squared and y equals 8 minus x squared using Riemann sums. Okay, why don't we use using Riemann sums with n equals to 3 maybe? No, let's do n equals to, what is it going to be? Probably, let's do n equals 2 rectangles, just to make it really simple. Okay, so what do we need to do for an area between two curves function? What we need to do is the integral from something to something of something minus something, right? dx. So that's a lot of question marks here. So we need to figure out each of these question marks one by one. And the first thing that I think we can try to figure out is, well, which one should come first between these two functions, right? Should we do x squared minus 8 minus x squared, or should we do 8 minus x squared minus x squared, right? And the question of which one comes first comes down to which curve is on top and which curve is on bottom. Okay, so let's draw a picture of what these two curves look like. The first one is easy enough. It's just a parabola with vertex 0, 0, right? So here's our x squared. What does 8 minus x squared look like? Upside down parabola with vertex at 0, 8. Okay? So here's 8. And then our parabola looks something like this, maybe. And so the area that we're looking for is this area here, right? So which curve is on top and which curve is on bottom? Well, 8 minus x squared is on top, x squared is on bottom, so we know it's going to be integral from question mark to question mark of, we know that 8 minus x squared is the top curve, and we're going to subtract the bottom curve, dx. And now we need to figure out, where should I start counting area and where should I end counting area? Right? Where should I start and end the counting of the area? Well, I don't want to get any of this area, right? This area is still sort of between, right? But this is the area which is enclosed by these two curves. So this is what I'm after. So I need to know, okay, when am I going to start counting and when am I going to end my count? Okay? So does anybody have a good way of finding out the x values, x1 and x2, where we're going to start and stop counting? Is there any way I can find out what those x values are?
Find points at which both where each parabola crosses.
Yeah, we need to find the point where the two parabolas touch. If two parabolas touch, then that means that they have the same x value and the same y value, which means that if I plug x1, or if I just plug x into the x squared, okay, if I plug this x value in, I should get the same height if I plug it into x squared as if I plug it into 8 minus x squared. So I just set those two things equal to one another. And then I just get, what, 2x squared equals 8, and therefore x squared is equal to 4, and therefore x is equal to either positive or negative 2. So this is how I find out the bounds. So what do we think? Integral from 2 to negative 2 of 8 minus x squared minus x squared dx. Are we happy with this?
No,
Why not?
the second part should be in parentheses, right?
Okay, well, sure, yeah, we could put that in parentheses. You're right. Is there anything else wrong with this? No, not derivative. That's right. The negative 2, I put it on the top here, just to sneak something by you. We should remember, we always count from left to right, okay? Which means we start at negative 2, and we go until we hit 2, okay? And the integral goes from bottom to top, okay? So we start at negative 2, and we go until we reach 2, okay? So that was just a small difference there. If I had kept the bounds as they were, then I would have just gotten the negative of what I'm looking for in the end, right? Because switching the bounds just changes the sign of this quantity. Yeah.
So will the negative bounds value always be at the bottom?
Well, it could be that you have two negatives. What's the difference is that the smallest number goes on the bottom and the biggest number goes on the top. So if it's negative 4 to negative 3, we'd put negative 4 here and negative 3 here, as long as we're accumulating in that direction, which most of the time we will be. So yes, the starting value is here and the ending value is here. Okay, so now we have the integral that we want to find, right? Which, of course, by the linearity, we can rewrite as the integral from negative 2 to 2 of 8 minus x squared. Actually, we can rewrite it as 8 minus 2x squared, right? dx. Now, we only know how to estimate this quantity right now. We haven't learned the technique on how to find the true area under this curve, right? But what we do know is how to do it using a Riemann sum. So I'm going to use maybe a left-hand sum with n equals 2 rectangles, and my a and my b are negative 2 and 2, so my delta x is going to be equal to b minus a over n, which in this case is 2 minus negative 2 over 2, which is 4 over 2, which is 2. So I know each of my two rectangles are going to be 2 units wide, which makes complete sense because I'm talking about a length here of 4, so if I use two rectangles, I'm going to have one for each. I'm going to have one on the left and one on the right that are 2 units wide, right? Okay, so in order to do this, okay, all I need to do is take two rectangles. I know both rectangles have width 2. So I'm going to do 2 times the height of the first one plus 2 times the height of the second one. So what should the height of the first rectangle be if I'm using a left-hand sum? It should be the height of this function on the left side of the first interval. So we have 8 minus 2x squared, which is some other function, right? So who knows what it looks like, right? I mean, we know what it looks like, but okay. My point is, we have some other function, and we're trying to do the Riemann sum for that function, which means we need to take the height of each rectangle to be the height of that function on the left side of the first subinterval, which that height will be given when I plug in negative 2, which is the left side of the first subinterval, into this function here. So I'm going to do that by just doing 8 minus 2 times, negative 2 squared, right? Okay. Something seems wrong here. Oh, wait, that makes complete sense. Yeah, and then I'm going to add Should have one more parentheses here, sorry. Okay, then for the second rectangle, its subinterval goes from 0 to 2. And so the height of that second rectangle should be whatever we get when we plug the left endpoint of that subinterval in for x in my function, right? That should be the height of the second rectangle. So its height should be 8 minus 2 times 0 squared, right? Because the left side of the second subinterval goes from 0 to 2, so it's 0. Okay, so in the end, I think this is just 0. And then this is going to be 2 times 8 is 16. Okay, so we've estimated the area between these two curves using Riemann sums. So let me maybe do a quick demonstration here using Desmos of what's going on here. So we had one function x squared, right? And we had another function 8 minus x squared. Okay? And we're trying to find the area which is situated between the two of them. Now we know we get that if we integrate and we subtract these two curves, right? Which is kind of like taking a Riemann sum, and the height of the rectangles is going to be given by the difference in the two curves on each subinterval. So the difference between the two, we would get one rectangle with, which is, well, they're touching, so it has no height. Okay, so we have one rectangle with no height, and then we have another rectangle for the second subinterval, okay, whose height is the difference between these two functions on the left side of this subinterval. So on this subinterval, the left side's here, so the difference is this height. So we get a rectangle whose height is going to be, 1, 2, 3, 4, 5, 6, 7, 8 units tall and 2 units wide. So we get a rectangle which looks like this. Okay, I'm not tall enough to draw this, but you see what I'm saying there? And the same way that you can visualize that, you can visualize it in the exact same way by saying, well, I'm going to make a new curve, which is what I get when I subtract these two, which is, of course, the curve that we found, 8 minus 2x squared, right? So you'll notice that the height of the green curve is 0 when the difference between these two functions is 0. And the height of the green curve is 8 when the difference between these two curves is 8. So if we find simply the area which is trapped between the green curve and the x-axis, it's going to be equal to the area which is trapped between the red curve and the blue curve. I'm seeing some looks of despair out there. How are we feeling about this? Complete despair? Okay. All right. Well, what we need to remember about this in the end, okay, is simply this formula, right? If we want to find the area between two curves, we put the top curve minus the bottom curve, and we integrate. How we find A and B for this problem, we had to find where do we start counting area and where do we end counting area. And from there, it's nothing but a Riemann sum, okay? So forget about the picture. All we want to do is estimate what is this integral. And the way we estimate the integral is always with a Riemann sum. We just take the height of the function either on the left or the right or the top or bottom of the interval, okay? And we make that to be the height of the rectangles, and we make the width of the rectangles to be just however many rectangles we have over our interval. We just divide them up evenly. Any questions on this example? Yeah, Gino.
Where did you get the -2 and 0 plug it in to when you add them together? And how did you figure out those two numbers?
So basically I'm doing a Riemann sum, right? From -2 to 2. And I have a function which looks kind of like this, basically. So I'm trying to find the area underneath this curve, right? This is the curve 8 minus 2x squared, right? Which I got by taking one curve and subtracting the other one from it. So I got 8 minus 2x squared. I want to find the area underneath this curve using a left-hand Riemann sum, using two rectangles. So one of the rectangles goes from -2 to 0, and one of the rectangles goes from 0 to 2. We agree? So the way I find the height of the rectangle on the left, if I'm doing a left Riemann sum, I just take the height of the function on the left side of this first subinterval. So that's why I plugged -2 into this function. But it turns out, of course, this function has height 0 on the left side of this interval. So we get two rectangles. One of them is just, well, it's not really a rectangle at all. It's just flat. And then the second rectangle is this rectangle. So this was our approximation of this area under this curve. I mean, it's not a great approximation, but it's what we get when we do a Riemann sum, left-hand sum with two rectangles. Did that answer your question?
Yeah, I realized that I asked the wrong question. Why would you plug it back into the equation? That's what it says.
Are you talking about this part here?
Yeah.
So this is how I found the height of the rectangle on the left side, right? The height of the rectangle on the left side is whatever I get when I plug the endpoint on the left into the function. So when I plugged -2 into the function, it was just because I didn't have a graph of what this function looked like yet. I just knew that it's a function. Whatever its height is on the left side is whatever it is, right? So I know that the width of this rectangle is 2, and its height is going to be whatever is the height of the function on the left side. So the way I found the height of the function on the left side was just by taking whatever that left endpoint was and plugging it in to the function. So this is exactly f of a, or f of -2, right? So I take the width of the rectangle 2, I multiply it times the height of the rectangle, which is whatever the height of the function is on the left side of that subinterval. Does that answer your question now? Yeah, Brendan.
So you would only use one Riemann sum, you wouldn't take the average in this case?
Well, if you do it the other way, you can, I mean, yeah, you'll get the same answer. So that's the thing. We proved, right, or well, we didn't prove, but we stated that this integral, right, if I do integral from -2 to 2 of, okay, let me copy this. So the question was, why would I just do one Riemann sum of this function instead of doing a Riemann sum for this function and then subtracting whatever Riemann sum I get for the other function? And the answer is because these two things are the same. So I can do one Riemann sum where I take the height to be the difference of these two functions. So the first rectangle looks like this, second rectangle looks like this, right? Or I can do two Riemann sums. The first Riemann sum being what I get when I take this rectangle and this rectangle for these two functions, and then I subtract what I get when I do the Riemann sum for the other function, which is this rectangle and this rectangle, right? But if I take these two rectangles and I subtract them from the bigger ones, maybe let me draw. So this is what I would get if I did the Riemann sum for the bottom curve. And then if I did the Riemann sum for the top curve, I would get this guy again, and then this guy, this orange piece, right? So it's a matter of difference of perspective of, am I gonna take two orange rectangles and then subtract this purple one? Well, if I do that, it's kind of the same as just not ever using this rectangle and just do the right orange rectangle. So you can do it that way, is the long, short answer to your question. Okay, any more final questions on this area between two curves problem? Yeah.
How did you know which function you were subtracting from the other? If you had it the opposite.
Great question. So the question was, how did I know that I put the correct function first? And the answer is the first function should be whatever function is on top. And I determined that visually by graphing the two equations. So when I graphed the two equations, I knew that 8 minus x squared looks like this, and I know that x squared looks like this. And when I look at their graphs, I can identify that the top function is that 8 minus x squared function. So that's how I know which one comes first. Yes?
So will the problems always give us like how many rectangles to use?
Yes.
Okay.
Yeah, the problem will always specify how many rectangles to use. Any final questions before we move on? Okay, to be honest, I mean, this problem is a little bit involved. I mean, I think for an exam problem, I wouldn't give something quite so open-ended as this. I would be a lot more specific, and there'd probably be some like intermediate steps where I'd kind of walk you through it on an exam or something like that. But again, area between two curves using Riemann sums is just kind of a pain in the ass. So I probably wouldn't ask you to do something quite this complicated on a quiz or a test. Okay, let's move on to the new material for today. Spent a little bit longer than I was planning on that. So for today, what we want to learn is how do I interpret integrals? Okay, so back when we were doing derivative problems, we had a lot of problems that were like, okay, find out what is f prime of 3 and interpret it in the context of the problem, right? So in that sense, when we had questions like that, we were trying to say, okay, we have a function, we take its derivative, we plug in a number, what does that represent? It represents the rate at which that function is changing at that point, right? So we need to now understand how are we going to take word problems involving integrals and understand what does integration mean in the context of the problem. So that is what we're going to work on today. And basically, there's not much to this section. There's just two things we need to learn. The first of which is, what are the units of an expression like this going to be? So if we take the integral from 0 to 60 of something and we integrate, we're going to get a number. And that number has a meaning in terms of the problem, and numbers should always have units. So we need to find out what are the units of an integral going to be. So the units of an integral from a to b of f of x dx are the units of f of x times the units of x. Okay, the units of f of x times the units of x. Okay, or if we're doing f of t dt, then it's the units of f of t times the units of t, right? So we take whatever variable we are integrating with respect to, we multiply that variable's units with the units of the function itself, and we get the units of this number. Okay, so for example, well, okay, yeah, let's do this problem as an example. Okay, a school bus going to travel with velocity v of t miles per hour. And the question is, why don't we start by answering what are the units? Of integral from 0 to 60 of v of t dt going to be? That's the question. The answer is, well, it's going to be whatever the units of v of t are times the units of t. So the units of v of t are miles per hour. So I take miles per hour and I multiply times the units of t. The units of t are minutes. So I get miles per hour times minute. Now I know a minute is 1/60th of an hour, so I could simplify this by saying this is miles per hour. Okay, and I multiply that times hour over 60. And I cancel the hours, and I get 60 miles over 60. Or 60th miles. Okay, so I get a unit of measurement, which is the length 1/60th of a mile. Okay, so I just take the units of the function and I multiply them with the units of the variable which I am integrating with respect to. Okay, and now the second part of, that's really the first part of this section, and the second part is, okay, we know what the units are, but what does it mean? So the second part is interpretation. Okay, so this is maybe the most important part for this section, which says if f of t is a rate of change of a quantity, then the integral from a to b of f of t dt is the total change in that quantity from t equals a to t equals b. Okay, so if f of t is a rate of change of a quantity like velocity, or the rate at which a population is dying, or the rate at which I am, doing anything, right? Then when I integrate that rate of change, okay, then from A to B, I get the total change in that quantity from A to B. So I accumulate that rate of change over a space of time. This is kind of like, can be compared with, okay, I travel 80 miles per hour for 1 hour, i.e. I traveled 80 miles, right? With that first thing we were doing in the first section, we're gonna accumulate this area under the curve is gonna represent the total change in this quantity when we integrate a function which is a rate of change. So let's see how it works for an actual problem. Well, our school bus here is traveling at v of t in miles per hour. Is v of t a rate of change? It's a rate of change of what substance? Distance, right? It's the rate of change of distance. So if I integrate from 0 to 60 of v of t dt, then I'm going to get the total distance traveled from t equals 0 to t equals 60. Okay, so all I'm doing here is I'm just gonna I'm gonna rewrite this statement, okay, using v, okay? So I'm supposed to do the integral from 0 to 60. So I'm gonna put 0 where a is, I'm gonna put 60 where b is, and I'm gonna put a v where the f was. So the integral from 0 to 60 of v of t dt is going to be the total change in that quantity. Well, I know what that quantity is. Total change in distance from t equals 0 to t equals 60 minutes. In other words, it's how far the school bus drove in 1 hour. Total change in distance from t equals 0 to 60 minutes. Hi.
102.
Sorry?
This is 102.
What about 102?
Do you have a flash drive or external hard drive up there?
There is an external hard drive here.
Okay, sorry to bother. I'm from upstairs, volume. Sorry, guys. I gotta get it for another lecture. Thank you so much.
I was so confused if she thought that like 102 was the class number, or if this is the, I guess we're in room 102, aren't we? Okay, that makes a lot more sense. All right. Where were we? Miles per hour. How far do we go in 1 hour? You guys have seen that video, right? Of like that viral video of the person who's like asking their friend this question in the car. Do you know what I'm talking about? And they're trying to think like, they're trying to figure out how far they'll go in 1 hour if they're going 80 miles an hour. And they're just totally like stumped. And they're trying to think like, well, if the circumference of the wheels of the car is probably like 3 feet, and there's 5,280 feet in 1 mile. Oh man. That was a classic. You got to see it. If you haven't seen it, you're missing out. Okay, so any questions on this first problem where we interpreted? First, we found out what are the units of this thing, and then we tried to interpret what it means in terms of the problem. All right, if there's no questions, then we're going to do a little bit of group work today. So what I want you all to do is get into groups, okay? And for part B, C, and D, I'd like you to find the units of that integral, and I want you to interpret what the integral means in terms of the problem. Okay, so go ahead and groupify. And if your group has any questions about anything, just raise your hands, okay? part, why don't we just start with defining the units of this thing, right? We take an integral, right? We integrate the rate of change d here with respect to time. So how do we find the units of an integral? From what we were discussing just a minute ago. So we scroll up like points there, right? On the box, right? Integral units are going to be given by what? Yeah, it's going to be, we take the units of the function we're integrating, and we multiply times the units of the variable which we're integrating with respect to. So in this case, exactly. So we take the units of d, right, which is grams per hour, and multiply that times hours and get. So okay, so we integrate rate of change, right, or just any, integrate any function. This is a process which is done, when I say with respect to a variable, what I mean is, you see how I put dt, that tells me we're integrating with respect to t. So the units of this number, right, I do the integral from 3 to 5 d of t dt, I get a number, we want to know what are the units of that number. And the units of that number are going to be whatever the units of the function are. We multiply those units times the units of the variable. So if it's integral f of x dx, we take the units of f of x and multiply by the units of x. Or if it's d of t, we take the units of d of t and multiply times the units of t. So in this case, the units of which t is measured is grams per hour. Yeah. Well, no, d of t as a whole is measured. So this, if I plug a time in d function, what do I get out? I get a number which represents the rate at which the drug is leaving the system in grams per hour. So d of t is going to be grams per hour, and then the units of t are just hours. So I take grams per hour. Yeah, try to do B, C, and D.
Do we also just find the university as well or something?
Well, you don't need to solve anything. Just find the units and then interpret what the integral means. Yeah, we take grams per hour times the grams, right? Exactly. So I get a number, and that number represents the units. I want to think about what does that number mean in terms of this circumstance of leaving the body. What does that number represent? Oh, I just found this one thing. I think, yeah, I just found this as a front of our class, like on the first day of class. I don't know. It's like a fidget spinner. Okay, let's come back together as a group. I saw a lot of good work out there. So I just want to reiterate what we were talking about here, right? So we want to do basically these two steps for each of these problems. So the units of any integral are going to be just whatever the units of the function are, right? So this is a function. If I plug x into it, whatever x is, then I get an output of a number, and that number has units, okay? Whatever f is measuring. For our, okay, why can I not move the screen sometimes? That makes me so upset. Hello. Okay, Jesus. Okay, so what are we measuring here? Well, d of t, okay, is measuring the rate at which the drug is leaving the system in grams per hour. So the units of this integral are going to be the units of d times whatever the units of the input are, which for our case is t, right? So I need to take the units of d of t, which is grams per hour, and I need to multiply that times whatever the units of t are. And t, it says, is measured in hours. So I do grams per hour times hour, and I get grams. So I integrate the rate of change of this drug leaving the system from 3 to 5 with respect to time, and I get a number, and that number is an amount of grams. Now, what does this amount of grams represent in the context of this problem where drug is leaving the body? It's the quantity of what? Sorry? Drug left in the system? What does D measure? It's the rate of change at which the drug is leaving the system. So it's not the amount remaining in the system. It's the amount that left between minutes 3 and, or wait, is it minutes? Hours 3 and 5, okay? So it's, I mean, you could interpret it as, so it's the rate of change of what? It's the rate of change at which the drug is leaving the system. Okay, so if we integrate a rate of change, we get the total change in that quantity. So D of t is measuring the rate at which what? The drug is leaving the system, which is a rate of change in the amount that has left. That is the amount that is changing. Okay, so we get the total amount of drug which left the body from hour 3 to, okay, I should say from t equals 3 hours to t equals 5 hours. So if you call 0 to 1 the first hour, then we're going for the, what? It's the 4th and 5th hour that the drug was in the system. Okay, any questions on this first one? Okay, so it can be a little bit tricky to get this interpretation right. Okay, especially when sometimes we're measuring the rate at which something is entering the system, and sometimes we're measuring the rate at which it's leaving the system. So it can be a little bit confusing sometimes, but we just got to go back to what does this word problem say? It says that d of t is the rate of change. It's the rate of change of what? Whatever it is the rate of change of, then when we integrate, we get the total change of that quantity, where the quantity here is, of course, the amount of drug which has left the system. Okay, so it's a little bit different because sometimes we do have these problems where we have a system that's describing the amount of drug left in the body, right? So two different situations there. Any questions on this one? Okay. Dude, I am gonna flip out if I can't move the screen. Please. Okay, here we go. So, next one. Integral from 100 to 200 of P of Q dQ, where P of Q is the marginal profit. Is marginal profit a rate of change? Yes, it is. It is the rate of change of the profit, right? So if I integrate a rate of change of profit from 100 to 200, what am I going to get in terms of my interpretation?
Profit.
It's going to be the total change in profit, right? Total change in profit. And then how do I interpret Q going from 100 to 200?
Quantity of an item being sold.
Yeah, when Q increases from 100 to 200. In other words, what's the difference in my profit if I make 200 units versus if I make 100 units? We get the total change in how much profit. I'm going to make some amount of profit with 100 units, and then maybe I have a much bigger profit when I make 200 units. And we want to know what is the difference between them, right? In order to find that, we integrate the rate at which the profit is changing to find the total change in the profit from 100 to 200. That means quantity increased from 100 to 200. We check how did the profit change during this time. So what are my units? Well, the marginal profit is typically given in, okay, I guess it's not really that clear. It's probably dollars per unit. And then I multiply that times the unit of Q, which is just units. Okay, so I get dollars per unit times the number of units, and I end up with an amount of dollars, right? So, total change in my profit when we increase production from 100 units to 200. Any questions on this second one? A little bit different. Yeah.
You can also say it's the total change in profit when 100 additional items are sold.
Yes, but if you say I'm going to produce an additional 100 items, then how many items was I starting with is still a bit of a question, right? I increased production by 100. From what, right? From 1,000? From 1,000,000? Where am I starting this addition? So yes, but you need to specify a little bit more than what you said. Any other questions? How much time do I got? 15 minutes? Okay, so let's move on to part D. Okay, small Arctic city measures the amount of snow that they get over a given day. And they say that the snow is falling at a rate of S of t centimeters per day, where t is in days, since January 1. And we want to interpret, what does integral from 0 to 30 of S of t dt represent? Who can tell me what the units are going to be? Units are going to be, of course, centimeters per day times day, right? The units of the function we're integrating times the unit of the variable. So we get just centimeters. So I get a number of centimeters, which is describing something about snowfall when t goes from 0 to 30 and t is representing days from January 1. Who can put it all together for me for an interpretation?
So, I guess ST times DT represents the change in the amount of snow in centimeters over 30 days.
Yeah, total snowfall, right? In January. Right? Total snowfall in January. Okay, so we have a rate of change. We integrate the rate of change, we get the total change, right? The total change in how much snow fell is just whatever we call the total snowfall in that month, right? Any questions on part D? Okay, much the same to the other parts. Okay, let's move on and try another problem. And we're going to do this one together because I think it's hard. Okay, so it's a little confusing. Why is this confusing? It's confusing because B of t, okay, we have a runner's heart rate is changing at a rate of B of t beats per minute per minute. Okay, so when B of t is 10, then that tells us that the runner's heart rate is currently increasing at a rate of 10 beats per minute, which means that if all else is held equal, 1 minute later, their heart rate should be 10 beats per minute faster than it is presently. Okay, so a little bit confusing here that we've got per minute, but this is really kind of like describing the acceleration, if you will, of their heart rate, right? Okay, so t is in, oh, it's even more confusing. T is in 10-minute intervals since they started running. Okay, and we want to use the graph below to find when is their heart rate going to be the highest. Okay, when is their heart rate going to be the highest? So I think this problem is a little bit of a trick question, because it kind of makes you think, okay, when is their heart rate the highest? Maybe what I'll do is I'll just take a look at this graph and I'll just find the point where the function is the highest, and that would be the highest heart rate. Except we need to remember that B of t is measuring the rate of change in the heart rate. So if the rate of change is positive, the heart rate is still increasing, right? So even though here the function is positive, so the heart rate is still increasing as we go from minute 20 to minute 30, right? And as we go from minute 30 to minute 36. Yeah.
So would it be easier to look at this like a derivative graph to say that it's still positive since it's
Exactly. That is exactly what we're doing here. All of today has been about integrating a rate of change, right? Rate of change is the word that we are always talking about when we're talking about derivatives, right? So we are integrating derivatives. If you integrate a derivative, then you get some information back about the original function. So yes, what we want to think about, okay, is we are accumulating area as we move forward. And the question is a question about when is their heart rate the highest? Well, we start at a certain heart rate and then we accumulate area, and all of this area which gets accumulated is the total change in their heart rate, right? So if we want to look for when is their heart rate going to be the highest, we want to look for the moment where their heart rate has accumulated the most positive area, which it looks like it's going to occur at roughly 36 minutes. Okay? Because integral from 0 to 36 of b of t dt is the largest value of any integral of the form 0 to a of b of t dt. So the question is, okay, we can accumulate an increase in my BPMs over a certain amount of time. How long do I keep accumulating for in order to maximize the heart rate? Well, I just need to maximize the amount of positive area which I have, which happens when I go from 0 to 36, right? And then after that, okay, b of t becomes negative. That's not because we have a negative heart rate. That means that our heart rate is decreasing, right? And the rate at which it's decreasing is proportional to how low this number is. So the heart rate starts to decrease here, and it's decreasing faster and faster because the height of the rate of change is going down. Okay, so let's try to estimate their heart rate after they've been running for 40 minutes. Well, I know that their original heart rate is 80 beats per minute, right? And then they accumulate this total change in their heart rate, right? So all I'm going to do to estimate their heart rate after they've been running for 40 minutes is take our starting heart rate, 80, and I'm going to add to that the total change in heart rate from 0 to 40, which is the integral from 0 to 40 of b of t, which is the rate at which the beats per minute is changing. So I get b of t dt, and of course the units of each of these are in BPM, right? Because the units of b of t dt are BPM m, or BPM squared. How do we, okay, why don't we do b over m? Beats per minute, like that, and then the units of this one are beats per minute, which is beats per minute squared, times minute. Now if I do beats per minute times minute, what do I get? Just beats per minute. So these units match up. And how can I estimate what is this integral here from 0 to 40 of b of t dt? Yeah, I can try to estimate this area under this curve, right? Well, I just need to count up what is the area of one box, right? The area of one box is going to be half of a unit of time, which is 5 minutes. So that's 5 minutes wide. Okay. And then it is 5 beats per minute squared high, right? So each box has area 25 beats per minute. And if I want to estimate how much heart rate was accumulated, it seems like this person's heart is just going to be beating way too fast looking at this, because it's going to be 25 for each of these. Okay, well, this person is some kind of Olympian or something, because their heart rate is going to be like 600. Okay, so anyways, all we need to do is count the boxes. How many boxes do I have? I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I've got some pieces, right? This one's maybe 8.3. This one's maybe gets, 9.3. This one maybe gets me the rest of the way to 10. This one maybe gets me the rest of the way, or to like 10.3, and then 10.7, and then 10 or 11.1 maybe. I'm just adding little pieces of area by estimating. It looks like a certain amount of a box. So maybe this one gets us to like 11.4. This one gets us like 12.2. 5 maybe. Then add about 70% of this box to that. We get 13 points. Well, what am I doing? 13.2, right? And then what do I do with these lower boxes? Am I going to keep adding? No, I'm going to subtract their area. So together it looks like they make about one box. So I would say that it's going to go down to about 12.2, right? So we have, each box is 5 minutes wide, and each box is 5 beats per minute squared high, which means that we're going to take the number of boxes which is 12.2, and multiply it times the area of each box, which is 25. And this is going to get us our total change in beats per minute. Okay, so if we take their original beats per minute and we add this number, right, then we're going to get their ending heart rate. Which, as I said, I think is going to be really, really high based on this graph. Okay, any questions about how I worked through this problem? Let me recap what I did really quickly. If I have time, I do. Okay, so first, we needed to recognize that this function is a rate of change. When we integrate a rate of change, i.e. we calculate the area under this curve minus the area which is between the curve and the x-axis below, then we are going to get the total change in that quantity. So to find the quantity at the end, we just take whatever the quantity was that we started with plus the total change in that quantity over that interval, and that's going to give us an estimation of their heart rate after 40 minutes. So this is kind of like doing a Riemann sum, only instead of doing rectangles, I'm just kind of approximating the area of one box, and then I'm counting, or trying to count, roughly speaking, the number of boxes that I have under this curve. Any questions about this problem? Yes.
So at the end, you subtracted the area beneath the curve?
Yes.
Under the x-axis?
I subtracted
Or I guess
this
above.
area here from this area here. Okay? So we take the area on top minus the area on bottom. Any other questions?
So wouldn't it be more like, so you got 13.2 originally, and then that's why you got 12.2?
Yeah, because I subtracted this area, which looks like if you added up these two boxes, they would make about one box. So that's how I got 12.2 from 13.2. All right, we're done for today. If you have any questions, then you can stay after class, where I have office hours today from 3 to 4:30.
I have my quiz in here.
Sorry?
I have that quiz that's missing. I said I have it in here.
Oh, cool, yeah.
I remember you asking one day.